Okay, so in the last lecture, in the last two lectures, we saw second proof of finiteness of class groups. So in the first of those lectures, we proved using geometry of numbers that ideal class group of a number field is finite. This was done using an arbitrary set S, which is bounded, closed, convex and symmetric about origin. And in the second of those lectures, we made a good choice of S so that we get a nice constants in our proof. Now, today we are going to do something slightly different, as I promised last time. We are going to prove Dirichlet's unit theorem. And again we will use geometry of numbers, so it makes sense to do it in the same place as the proof of finiteness of class group. So, let me give you the statement of Dirichlet's unit theorem first, and then I will make many comments, some of them now, some of them later on. So, this is called Dirichlet's unit theorem. Dirichlet proved it more than 150 years ago. So, let K be a number field then if you look at units in K, okay, so star here means units. So, these are all x in OK such that there exists y in OK with x y equal to 1. This you can take as an exercise is same as saying set of all x in OK such that norm from K to Q of x is equal to plus or minus 1. Okay, so this is an easy exercise if you like. So what does the theorem say? It says that the group of units in K is a finitely generated Z module generated abelian group or Z module they are the same thing. Z modules are abelian groups and abelian groups are Z module. In fact, what you can say more, if you torsion out by, if you mod out by torsion of OK cross, then this has rank R1 plus R2 minus 1. Okay. So, what is torsion? This is torsion of OK cross, which is equal to set of all x in OK cross such that there exists n bigger than or equal to 1 with x to the n is equal to 1. Okay. So, this n depends on x that we are taking. Okay. In other words, these are roots of unity because we are in a field. Now, as I said, I want to make various comments about this. OK is a finitely generated abelian group. We saw that earlier. It has rank n. That does not mean that OK cross will be finitely generated abelian group, okay, a priori. You could have, OK could have, I mean many things can go wrong. For example, there could be infinitely many torsion points, there could be infinitely many roots of unity in K, and that would mean that OK cross will not be finitely generated. Or it could have infinitely many non-torsion points as well. A priori, neither of them is ruled out just because OK cross sits inside OK. So, this is you should think of this as a highly non-trivial theorem. So, this is the second non-trivial theorem that we prove in this course, the first one being finiteness of class group. Okay. Now, let me make some comments orally about how this this kind of phenomenon is part of a much more general framework in number theory. Okay. So, this part is not strictly necessary, but it is just for if you study more advanced topics in number theory, algebraic number theory, then you will see that you have seen these kind of things in a more basic setup. So, if you study the theory of elliptic curves and if you look at points of elliptic curves over number fields, so just say over rational numbers, then there is one important theorem about it and one important conjecture about it. The theorem about elliptic curves is called Mordell-Weil theorem. So, for rational numbers it was proven by Mordell. It says that the points on elliptic curves, rational points on elliptic curves, forms a finitely generated abelian group. Okay. So, one should think of that theorem as an analog of Dirichlet's theorem. And then there is a conjecture about elliptic curves which is part of the Birch and Swanerton-Dyer conjecture. It says that the Tate-Shafarevich group of an elliptic curve over rational numbers is finite, and you should think of that conjecture as analog of the class group, finiteness of class group. So, you see very quickly these two theorems that we prove for number fields, they become highly non-trivial. And in fact, in one of those things we do not even know how to prove finiteness of the Tate-Shafarevich group in general. Okay. In any case, that is that much for the digression and general motivation of why one should understand these theorems very well, because they form the first step of a highly non-trivial framework in arithmetic geometry, algebraic number theory. Okay, and now we go on to the proof, and as I said, I am going to again use geometry of numbers to prove this. So, the most relevant part here, the biggest idea is we define what is called Dirichlet's regulator map. And it is often denoted by lambda from OK cross to R to the power R1 plus R2. And what is this map? This map takes any alpha and sends it to log of mod of sigma I alpha. So, let me remind you what sigma I is. So, sigma 1 up to sigma R1, these are real embeddings of K, and then sigma R1 plus 1 up to sigma R1 plus R2, these are distinct complex embeddings. So, pairwise they are not complex conjugations of each other. So, okay, maybe just to make it somewhat less ambiguous, I'll write it as sigma R1 plus 1, sigma R1 plus 1 bar, and so on, sigma R1 plus R2, sigma R1 plus R2 bar, bar being the complex conjugation. These are distinct complex embeddings of K. Okay. So, this is a notation that we have seen before. Okay. Now, as is usual, I am going to we are going to prove this in many steps. Now, what I do is first I define H to be a certain subset of R1 R to the power R1 plus R2. So, this is X R1 plus R2 in R1 plus R2 such that summation I going from 1 to R1 Xi plus 2 times summation j going from 1 to R2 x R1 plus j, this is equal to 0. Okay. Okay. So, H is a subset cut out by a linear equation, one linear equation. So, this is what is called a hyperplane. So, H is a hyperplane in R1 plus R2. Okay. So, you see its dimension of H is R1 plus R2 minus 1. Okay. So, H is in fact a vector space. Okay. Not every hyperplane of course is a vector space, but H is a vector space because it is given by this particular equation, and its dimension as a real vector space is also R1 plus R2 minus 1. Okay. So, so that is okay. So, first claim that we are going to make is image of lambda is contained in H. Okay. So, image of lambda is a subset of H. Now, this is very easy to verify. How do you do that? Well, you take something in the image of lambda. What does that look like? Sigma 1 of alpha and so on, log of sigma R1 plus R2 of alpha. Okay. And I want to show that this is in H. So, I just take its sum. So, summation I going from 1 to R1 log sigma I alpha plus 2 times summation j going from 1 to R2 log of sigma R1 plus j alpha. Okay. And if you write this properly, then you get log of product I going from 1 to R1 sigma I alpha product j going from 1 to R2 mod of sigma R1 plus j alpha squared. And if you think for a second about what this is log of mod of norm from k to q of alpha. Okay. And by this easy exercise that I had in the statement of the theorem, this is same as log of mod of plus or minus 1, which is 0. Okay. All right. So, that gives us our claim that image of lambda is contained inside H. Okay. Well, and why is that a good thing? We want to show that we want, oops, it's going by itself, sorry. Yeah, we want to show that lambda has we want to show that image of lambda is modulo its image of lambda is a lattice in H. So, what we will show, so our claim is going to be that image of lambda is a lattice in H, and so that will show that image of lambda is a free abelian group of rank R1 plus R2 minus 1. And the next thing we want to show is that kernel of lambda is finite. Okay. All right. So, how do we show that kernel? Well, first of all, what is kernel of lambda? Kernel of lambda is exactly equal to OK cross or torsion of this. Okay. So, I defined this before, right. All right. So, why is this? So, it is clear that torsion of OK cross is contained in kernel of lambda, right. This is because mod of sigma I of alpha is equal to 1 for any alpha such that alpha to the n is equal to 1 for some n bigger than or equal to 1, right. So, if it is a root of unity, we know that mod of a root of unity is 1, and therefore, log of mod of sigma I alpha is also equal to 1, right. So, that shows that the torsion of OK cross is contained in lambda, right. And we want to show the other way around as well, right. So, if alpha belongs to kernel of lambda, then we know that log of mod of sigma I alpha is equal to 0 for all I. So, for all 1 less than or equal to I less than or equal to R1 plus R2. Okay. So, hence mod of sigma I alpha is equal to 1 for all i's between 1 and R1 plus R2. Okay. All right. So, this means that okay, so this means that yeah, so this means that kernel of lambda is contained in a bounded subset of OK. Okay, I am not saying OK cross now. I do actually mean OK, right? Because how did we show that OK was a lattice in R to the power R to the power n? We just used this map which sends alpha to sigma I alpha and sigma I bar alpha, and we showed that OK is a lattice in that. So, now we get that kernel of lambda is a bounded subset in this lattice, hence kernel of lambda is finite. Okay. Therefore, kernel of lambda is equal to torsion in OK cross. All right. So, that is how we prove that kernel of lambda is finite and its torsion, right, of OK cross. Okay. So, this means the upshot of this is that OK cross modulo torsion, which is the object that appears in statement of theorem, this is same as OK cross modulo kernel of lambda, and this thing is isomorphic to image of lambda. Therefore, if we prove the claim, we get our theorem that image of lambda is a lattice in in H. Okay. All right. So, there are two things we need to prove about to show that something is a lattice. One thing, so we will prove two things about image of lambda. A is image of lambda is discrete in H, and B is image of lambda spans H. So, these two things together will imply that image of lambda is a lattice in H, right. We had these three properties of lattice and we said any two of them implies the third one very early on in this course, and these are two of those properties. So, it suffices to prove these two properties. Okay. So, A is actually easy to prove. So, we will start with A. Okay. So, take a bounded neighborhood U of origin in H, then so this idea is very similar to the idea that we use for kernel of lambda. So, then sigma I of alpha is bounded for all i's between 1 and R1 plus R2. Okay. Therefore, yeah, I mean, okay. Therefore, U intersected with image of lambda is a finite set. Okay. And hence, image of lambda is discrete in H. Okay. So, that is one. Now, to prove B, it's somewhat trickier, and what we are going to do is we are going to show that there is no, so there is one non-trivial relations, linear relation between image of lambda in for the coordinates of image of lambda, and it is this linear relation that H satisfies. Okay, that defines H. We are going to show that there is no other non-trivial relation. Okay, so what I am going to do for B is the following. So, let lambda 1 up to lambda R1 plus R2 be real numbers not all equal, okay, which means that at least two of them are distinct. Okay. Then we show that there exists eta in OK cross such that I define this quantity f of eta, which is lambda 1 log mod sigma I eta up to lambda R1 log mod sigma R, sorry, this should be sigma 1, this should be R1 eta plus 2 times lambda R1 plus 1 log sigma R1 plus 1 eta and so on lambda R1 plus R2 log sigma R1 plus R2 eta. This quantity is not equal to 0, okay, which means that there is no other linear relation that all elements in image of lambda satisfy except the one that defines H. Okay. So, how do I prove this? Well, I just have to construct this eta, and constructing units is not easy, and this is the reason why this statement is so amazing and non-trivial to prove. Okay, so what I do is I take, okay, so let rho 1 up to rho r1 plus r2 be positive real numbers such that I am going to make a choice of precise choice of them later on, but right now I just want them to satisfy this property. This is equal to 2 by pi r2 mod of dk to the half, and let me call this quantity A. Okay, so this quantity is capital A. Okay. All right. So, so this is this quantity. Now, as I said, I am going to make a precise choice of these rho i's later on, and let S be the, this is where the geometry of numbers comes into picture. So, these are all x1 up to x r1 plus r2 in r1 plus r2 such that mod of xi is less than or equal to rho I for I between 1 and r1, mod of xj squared plus xr2 plus j squared is less than or equal to rho j squared for r1 plus 1 less than or equal to j less than or equal to r1 plus 2 r1 plus r2, not 2r2, sorry, r1 plus r2. Okay. So, that is how I define S. Now, again S is bounded, closed, convex, symmetric about origin, in r to the power r1 plus r2, right. Furthermore, volume of S, we have computed this before in some sense, volume of S is simply equal to 2 to the power r1 plus r2 mod of dk to the half. And if you like, you can take this as an exercise. It is not a hard exercise at all. This is just the way the rho i's are defined, and the computation and the way the discriminant is defined. Okay. So, it is a good exercise to do. It is not difficult. You will be able to do this exercise easily if you have understood the course up to now. Okay. All right. So, what does this mean? So, by geometry of numbers, this means that S intersected with OK is bigger than let me say, contains a non-zero element, contains a non-zero alpha. Okay. So, that is what it means. So, what is that? This is sigma I of alpha is less than or equal to rho I for all i's between 1 and r1 plus r2. Okay. So, that is fantastic. Now, because alpha lies in S, as alpha belongs to S, norm of alpha is less than or equal to A. This is just because these rho I, rho 1 up to rho r1, rho r1 plus 1 squared up to rho r1 plus r2 squared is less than or equal to A. But now, as alpha belongs to OK, norm of alpha is bigger than or equal to 1, right, because it is an algebraic integer, its norm has to be an integer. So, it is bigger than or equal to 1, and so we end up proving the following. So, hence you put these two things together, we get norm of norm, okay, I should write it in the following way. Sigma I alpha is bigger than or equal to A inverse rho of I for 1 between I and R1, and then sigma I alpha is bigger than or equal to A inverse rho I squared for R1 plus 1. Okay, let me write it neatly. R1 plus 1 less than or equal to I less than or equal to R1 plus R2. Okay. So, so there is a lot of this proof left. So, I think this is a good point to stop in this lecture, and we will continue the proof in the next lecture. So, let me just recall what we did. We want to prove Dirichlet's unit theorem, and to prove Dirichlet's unit theorem, the most important idea is to define this Dirichlet regulator map, which goes from OK cross to R to the power R1 plus R2, and we are going to prove two things about this map. The first is that kernel of this map is finite, so we proved that today. The second is that image of this map is a lattice in a certain hyperplane, and to prove that it is a certain hyperplane, we look at the we show that the image is discrete, and we show that the image spans this hyperplane. So, today we proved that the image is discrete, and we are in the middle of proving that it spans the hyperplane. So, the idea for that is to show that it does not satisfy any linear relation except the one that defines the hyperplane, and so this is what we are going to prove next time. Thank you.